There are many techniques to convert an equation from standard expanded form to factored form. So far, we've learned common factoring, decomposition, and the sum and product method. And so that leaves us with our final method for factoring called difference of squares. As a warm-up, we are going to multiply two binomials that are opposite factors. We consider them to be opposite factors because of the opposite operations that are found in each bracket. As we multiply these two binomials together, you should see that there will be a pattern that emerges in the answer that you get. So if I use the FOIL method to expand my two sets of brackets, I get x squared plus 3x minus 9. And if I collect like terms, I can put together these two middle terms here that both have x's, and that's going to leave me with x squared minus 9. So you can see here that the terms that have the x variable, they are eliminated or they disappear. And so you're only left with a term that is squared, a subtraction sign, and a plain number on the end. With our second set of binomials, if we were to expand them out using the FOIL method, we would get 9 minus 6x plus 6x minus 4x squared. And again, if we were to collect like terms, we would be left with 9 minus 4x squared. So the pattern that you should notice is that you get an answer that has only two terms that are separated by a subtraction sign, and the term that has a variable is squared. And is there anything special that you notice about the numbers? So we've got a 4 and a 9 in this example. And in our previous example, we ended up with a value 9. So it's not necessarily that we got the number 9, but what type of number is the number 9 or the number 4? These numbers happen to be perfect squares, meaning that if you were to square root 9 or if you were to square root 4, you would get a nice whole number, not a decimal answer, meaning you can take the square root and get a whole number. So that takes us to our steps for factoring by using the difference of squares method. There are a couple of criteria that need to be met before you can proceed to factor the quadratic equation or expression using the difference of squares method. The first is that your equation or your expression should only have two terms, meaning it should be a binomial. And each of those terms should be a monomial squared, meaning there should be something squared in the equation. And the terms must be subtracting from each other. Remember, the word difference typically means subtraction. In order to then factor your expression, you are going to find the square root of each term, and you are going to take your answers after taking the square root, and you're going to insert them in a set of brackets. So similar to like what you saw using the sum and product method, you're simply going to create yourselves two sets of brackets, and you're going to place your answers or your magic numbers, if you want to call them that, inside those brackets. So let's take a look at our first example. Now remember, regardless of the type of question that you get, if you are looking to factor, you first need to check for a common factor. So if I look at the two terms in my equation, I've got an x squared and a 25. Okay, so there is no common factors between x squared and 25. So nothing I can do there. The next thing I might want to try to do is check if I can factor this using decomposition or the sum and product method. Now, what you should notice right away is that this is an equation that only has two terms, whereas equations that can be factored using decomposition or the sum and product method typically have three terms. They are trinomials. So those two methods are not going to work for this equation either. So that leaves us with difference of squares. Now let's check and make sure that this actually meets all of the criteria in order to perform the difference of squares method. So criteria number one, there has to be two terms, and we definitely have two terms. One of the terms needs to be squared. So we have our variable x squared, so that's good. There needs to be a subtraction sign between your two terms. We have that. And any values or numbers that are in your equation have to be perfect squares, meaning you can take the square root of the number and get a whole number as your answer, not a decimal number. So we've got the number 25, and 25 is a perfect square. If you take the square root of 25, you will get a nice whole number. Okay, so this question definitely meets the criteria for difference of squares, so we are ready to begin factoring using that method. So what we need to do is take the square root of each term inside our equation. So when we report our final answer, we're going to put 0 equals. You're going to open yourself up 2 sets of brackets. And now we're going to begin performing the square rooting. So let's start with the square root of x squared. So the square root of x squared is simply x. So you are going to place an x inside each bracket. Now, in terms of the operation or the signs that go inside each bracket, remember the warm-up that we did on the top of the handout, and we looked at expanding or foiling brackets or binomials that had opposite operations, meaning one bracket had a subtraction sign, one bracket had an addition sign. So that is one of the other noticeable patterns that has to happen in your answer when you are factoring using a difference of squares. You're going to have one bracket with a subtraction sign, one bracket with a plus or addition sign. And then finally, we are going to end off by taking the square root of 25. So the square root of 25 is 5. So you're going to put a 5 inside each bracket. And that is your fully factored answer, x minus 5 multiplied by x plus 5. Let's take a look at our next example. We've got 0 equals x squared plus 36. So immediately, now that students get the hang of difference of squares, they think, this has got to be a difference of squares question. I've got 2 terms. I see that one of my terms is squared. 36 is a perfect square number. You can take the square root of 36 and get a nice whole number. So it's got to be difference of squares. But what is the key thing that is missing here, or that is not available in this equation? Think of the word difference. Difference means subtraction. But if you look at your equation, what do you have between your 2 terms? You've got a plus sign. So yes, this may meet all of the other criteria for difference of squares. However, it doesn't actually have a subtraction sign between the 2 terms. So because of that, this cannot be factored using the difference of squares method. All right, so if we do still need to factor it to come up with an answer, let's go back and try one of all our other methods that we've learned. So we could try common factoring. So are there common factors between x squared and 36? No, there's nothing in common, nothing that we can pull out or remove here. Okay, so that leaves us with a decomposition or the sum and product method. Now, if we look at our a value, meaning the number in front of or attached to the x squared, your a value is 1. So because your a value is 1, we can try to factor this using the shortcut, the sum and product method. So I'm just going to give myself a little bit of space here. Okay, so we're going to try factoring this using the sum and product method. So we have a c value of 36. So I need to think of 2 numbers that are going to multiply to give me 36, and they have to add together to give me my b value. Now, if I go back and look at my equation, there is no middle term. Usually we're used to seeing x squared and then a term with an x in the middle, and then the plain number attached to the end. However, we don't have a value in the center of our equation. So when you are missing a value in the center of your equation, that means your b value is 0. So we have a c value of 36, but we have a b value of 0. So we need 2 numbers that are going to multiply to give us 36, but they have to add together to give us 0. So take a few seconds, think of what number combination could work for this scenario. Okay, so let's try 6 and 6. So I know that 6 multiplied by 6 is 36. However, 6 plus 6 is not going to give me 0. That's going to give me 12. Okay, so 6 and 6 are not going to work. So what else could I multiply to give me positive 36? Well, what if I tried negative 6 and negative 6? So negative 6 times negative 6 is a positive 36, so that works. But if I add those two numbers together, negative 6 plus negative 6, that's actually going to give me negative 12. So that combination is not going to work either. So you could try to think of all the other multiplication factors that would multiply to give you 36. I mean, we've tried 6 and 6. You also have 1 and 36. You've got 2 and 18. You've got 3 and 12. You've got 4 and 9. Whoops, sorry. You've got 4 and 9. So while there are lots of combinations that can multiply to give us 36, none of these combinations are going to add together in any way, shape, or form, even with a variety of positive and negative signs. They're not going to add up to give us 0. So this is not a difference of squares. There is no common factor that we can pull out. We can't use the sum and product method to factor it. So nothing really we can do here. So all you can say is that this is not factorable. And there will be equations that you come across from time to time that cannot be factored using one of the 4 methods that we've learned. All right, let's move on to our next example. We want to factor this expression, 25n squared minus 169m squared. All right, so we want to check, is this potentially a difference of squares? Well, does it meet our criteria? We've got 2 terms. We've got terms that are squared, and it's okay that there's a squared term in the first term and in the second term. That's okay. They are separated by a subtraction sign. That's good. And 25 and 169, are those numbers perfect squares? And yes, they actually are. You can take the square root of both of those numbers. So this is indeed a difference of squares factorable question. All right, so to prepare our answer, we're going to put in an equal sign. We're going to open up 2 sets of brackets. If you want to, you can put in a plus sign and a minus sign inside your brackets. The order doesn't matter. It doesn't matter if you put the plus sign first or the minus sign first, as long as the brackets have one of each. All right, now we're ready to begin taking the square root. So let's start with 25. We're going to square root that, and so that's going to give us 5. So I'm going to put a 5 inside each bracket. I'm then going to square root n squared. So the square root of n squared is n. And now that has to be directly attached to the 5 because the n squared was directly attached to the 25. They are one term altogether. So the square root results also have to be one term attached together. Okay, we've got our operator in the center. And now we're going to move on to the next set. So we've got the square root of 169, which is 13. So we're going to put a 13 inside each bracket. And then we have the square root of m squared, which is m. So our final factored answer is 5n plus 13m multiplied by 5n minus 13m. All right, so I've kind of moved my handout page over to the right side. I realized I missed question C up at the top there. So here are 3 other factoring equations or expressions. I'm going to ask you to pause the video and try to factor them yourself. See if you can pinpoint which method of factoring to use. Are all 3 of these questions examples of difference of squares? Maybe. Maybe not. That's going to be for you to decide. Remember to try to work your way through all the different types of factoring if you are unsure. So go ahead, pause the video, try to factor all 3 of these expressions, and then come back to see the solutions. All right, so here are the answers for each of these 3 questions. So up at the top, we've got 144 minus m squared. This is indeed an example of difference of squares. 2 terms, one of them is squared, separated by a subtraction sign. 144 is a perfect square. If you take the square root of 144, you do get 12. So we have our answer of 12 minus m and 12 plus m. With question B, this one is not factorable. So while it may look like a difference of squares questions, and it does meet the majority of the criteria for difference of squares, 149 is not a perfect square number. If you try to take the square root of it, you will get a decimal answer. Now, there are no other common factors that you can pull out, and this can't be factored using any of the other methods, so this one is not factorable. And in the last example here, this one is a difference of squares, believe it or not. Doesn't look like it from the beginning though. However, remember that no matter what question you are given, you always want to try to see if there is a common factor that you can pull out first. And there is a common factor for this expression. There is a common factor of 3. 3 can go into 3 and 3 can go into 27. So I have a common factor of 3 listed out here at the front. I pulled it out. If I were to divide both of these terms by 3, I would be left with x squared minus 9. This portion inside the bracket, x squared minus 9, is a difference of squares. Two terms separated by a subtraction sign. X is squared, 9 is a perfect square. You can take the square root of it. So if I were to perform the difference of squares, I would be left with x plus 3 and x minus 3.